Okay, so I wanted to make a quick video to give you an introduction to continuous probability distributions. So we were previously looking at discrete probability distributions, which were nice because in the discrete land, we were able to write down every possible outcome, right? Since they were discrete, usually they took countable values. So if we're talking about like in the binomial experiment, if there are 5 trials, we could end up with 0, 1, 2, 3, 4, or 5 successes, right? And it became very easy when questions were asked, like what's the probability that x is greater than 4, to sit there and go, oh, the only outcome greater than 4 is 5. Or have we been asked for greater than, say, 3 instead? Again, we're able to just sit there and go, okay, these 2 values are greater than 3, let's add them together. It was very tangible working in the discrete world because we could see every possible outcome. We could see every possible probability if we wanted to. We could make this table and visualize things. And now we're going to move into the continuous world, which is slightly more difficult. So our continuous variable that we're going to be looking at is this x given here, the weight of a newborn kitten in ounces. So I have this little example here. One way we could handle this is to make our variable discrete, right? Our weight of a newborn kitten in ounces is only continuous in its purest form, right? If we have a really, really good scale. But if we have a crappy scale, then we could probably just get a scale which rounded to the nearest ounce, or we could just take those numbers and truncate them by rounding to the nearest ounce. And we're basically making this variable into a discrete variable. And then we could make our cute table, right? I went ahead and instead of making a table, I drew up a quick histogram basically showing us what these values were. Now, I could have done this with the bar chart. I just wanted the bars shoved together because our variable is quantitative in nature. So you can see here the most likely outcome, the tallest bar, because we have our probabilities is the heights of the bars. Our tallest bar is at 3. And that's because the average weight of a newborn kitten is 3.4. So closer to 3 than anything else. So 3 is the largest bar, and then it sort of trickles away from there fairly symmetrically. So yeah, we've got this lovely distribution. And we can imagine if we got ourselves a little finer of a cut, say instead of rounding to the nearest full digit, maybe not rounding to the nearest tenth of an ounce, we might see something that looks more like this. So 3.4 is our average, so it's the most likely outcome, right? But then the next ones are going to be slightly less likely, but still likely, because a kitten could definitely weigh 3.3 or 3.5 ounces. And then it's going to continue to get less likely as we move away. And I'm hoping you guys can sort of see that this would symmetrically become less and less likely until it's impossible, right? For a kitten to weigh less than 0 pounds or more than whatever the fattest kitten weight happens to be. So this is actually what continuous variables are all about. Instead of being able to look at each particular outcome, we actually use a curve to model this. And we call this curve our probability density function. This is our probability density function. And this curve allows us to look at this and get particular probabilities out. Now, what this curve does not let us do, if we're looking at a particular outcome, say at, let's come over here to 4. The height of this curve at that particular value means nothing. It doesn't tell us anything because since every single possibility here exists, right, and this is on this continuous scale, the probability of getting any one particular outcome out of this infinite range of outcomes, right? There are infinitely many things within this range, is approximately 0. So the probability that x is equal to 4 is basically 0. So it has nothing to do with the height of this thing at all. It's more, one outcome we can't really do. What we can do, though, are ranges of outcomes. So the probability that x is greater than 4, this is something we can do. We can look at actual areas under the curve here. This is a probability that x is greater than 4, whatever that area under the curve is. So that's what we're going to be doing a lot of. So let's write down some properties of this probability density function. So our properties. The actual values of the function f of x have to be strictly greater than 0, right? We cannot have this under 0. They also actually need to be less than 1. That way when we sum things up, right, they're in there. But mostly this greater than 0 is important. It should be equal to. It can actually equal 0 if something can't happen. The bigger property, though, and the one that we're going to use to check things, is the area under the curve has to equal 1. So the whole area, this is every possible outcome, that's the 100% probability. That's our sample space, right? So the area under our curve is 1. And then we got this sweet property that we're going to be using it throughout this to actually find probabilities, and that's the probability that X falls into region. The region is equal to the area under the curve in that region, which is what I drew over there. Another cool thing about this, now that we're in continuous land, is we no longer have to pay a lot of attention to whether or not something has an equal to in it, because the area of having that probability of having exactly 4 is essentially 0. So this does not make any difference. You can do probability X greater than 4, X greater than equal to 4. They mean the exact same thing in the continuous land, where they meant very different things in our discrete land, right? Greater than equal to 4 was this, where just greater than 4 would only be 5. And they'd have very different probabilities. Now that we're in continuous land, these things are the same. So we're going to do one quick example from a very common continuous distribution or uniform distribution here, and that is the uniform distribution. So in this case, our probability density function is given by something like this. It's a piecewise function, if you hadn't seen that in a previous class. Piecewise means that it has one value at a certain area and then it has a different value at other places. So first thing I'm going to do is graph this so we can actually see what the heck this piecewise function is like. Because for those of you coming out of 92, you haven't seen this before. So a piecewise function. We have our x on the side, we have our f of x, or our y's on the y-axis. In this case, let's just go ahead and give our x values. Let's start at 0. And let's go up to 7, 1 past that little range of values given in that interval notation for us. And we know for our f of x, it's got to be strictly less than 1. And in this case, the greatest our f of x ever is 0.5. So if we want to graph a piecewise function, they're basically telling us for this range of x's, this is our graph. F of x is just 0.5. And this is what the uniform part of the uniform distribution is from 4 to 6, this thing is uniform. It is the same probability for every outcome, right? The density curve is the same thing for every outcome between 0 and 4. Everyone is equally likely. Now, outside of 4 through 6, from 0 to 4 and from 6 on, the probability is 0. It says 0 the rest of the time. So this is what our curve looks like. It's a little bit silly of a curve, right? But first thing we might want to do is to make sure that this is actually a probability density function. So we're going to check that this is a probability density function. And the way to check that is to make sure the area under the curve is equal to 1. Because if that's not true, this is not a valid probability curve. We can't actually do anything else. So this is why we do the normal distribution as our first introduction. Because areas under the curve technically mean integration, right? And this is an intro class. You did not need to take calculus for this. So finding an area under the curve, we're never going to actually integrate in this class, though you could. In this case, we can actually figure out the area under this in this curve, right? It's 0 on the outsides, but we can figure out this area because it's a rectangle. We know the height of this rectangle is 0.5. That's our y. And the length of this rectangle from 4 to 6, well, that's just 2. So if we want to check that our area under the curve is actually 1, we're going to use just the area of a rectangle to solve this. That's that's just going to be 2 times 0.5, right? Length times height, which is 1. Yay! We do have a valid probability density function. So now that we've confirmed that this is a real deal probability density function, we can go ahead and find some probabilities with it. So let's do as an example, let's figure out the probability that x is less than 5.5. And technically, this is the exact same thing as x being less than or equal to 5.5. So I'm going to just use a straight line here. 5.5, I'm going to draw a line. All right, that's 5.5. We want to know about the probability of being less than that. Well, that's just asking us for this area under the curve, right? Nothing else. Doesn't matter that we also are including less than 4 because that's 0. And now that's only going to change the length of our rectangle, right? The height stays the same. Instead of being 2, I've now cut it down to 1.5. So if I want to find the probability of x being less than or equal to 5.5, that's just going to be 1.5 times that height we had of 0.5, which is going to equal 0.75. And that's because we've shaded 3/4 or 75% of the actual rectangle. So that's a brief introduction to these continuous probability functions and distributions that we're going to be looking at. We are going to be looking at on class on Thursday the normal distribution, which has a nice pretty bell-shaped curve. And then when we're finding probabilities under that, we're going to have to be figuring out what the heck we do to get this. It's not as easy as finding the area under a rectangle, right? Because this is not a rectangle, not even a trapezoid. So that's why we're going to be using technology as well as tables in class on Thursday to figure out how to find those areas.